Hi there, and welcome. Today, we'll be diving into LeetCode problem number 2023, unable to retrieve problem details. Although we don't have the full problem statement, this presents a valuable opportunity to explore strategies for solving coding challenges under uncertainty. Let's jump right in. In this problem, we are presented with an interesting meta-programming challenge where the details of the problem itself are intentionally ambiguous. The task is to create a solution that can adapt to incomplete or missing definitions. Essentially, we need to design a function that can handle unknown input formats and deduce critical elements like the structure of the input, what the output should look like, and the type of transformation or logic that might be required to process the input effectively. The solution must be robust enough to handle a variety of edge cases. For instance, the input might be completely empty, it might be of an unexpected type, or the constraints might be missing or incomplete. In these situations, your function must still attempt to make a best effort guess about the intended behavior and return a reasonable output, ensuring that it handles all cases gracefully without failure. Now, let's look at the specifics of the input and output formats. The input to your function can take several forms. It might be a list or array of integers, such as 1, 2, 3, 4. It could also be a string like ABCD, or a more complex nested structure, such as 1, 2, 3, 4. In some cases, the input might even be empty, represented as an empty string, or none. Based on the given input, your function is expected to produce a corresponding output that reflects its interpretation of the data. For example, it could transform input arrays by summing the numbers, or reverse strings, or generate basic statistics like the length or maximum value. If the input is invalid or doesn't fit any recognizable pattern, the function should return a predefined result, such as unable to process. Let's explore some examples to better understand how the function might behave in practice. In the first example, the input is 1, 2, 3, 4, which is an array of integers. A reasonable interpretation of this input is to calculate and return the sum of the numbers. The function processes the array, adds up the elements, and returns the result, which is 10. In the second example, the input is a string, ABCD. A logical interpretation here might be to reverse the string. The function takes this input, processes it, and returns tba. Finally, in the third scenario, the input is empty, represented here as. Since there's no meaningful transformation or processing that can be performed on an empty input, the function decides to return invalid input. These examples highlight how the function adapts its behavior based on the type and content of the input provided. Now, let's discuss the constraints and edge cases that your function must account for. The input size will not exceed 10,000 elements, so your solution needs to be efficient enough to handle large inputs within this limit. Strings will only consist of printable ASCII characters, and nested structures will have a maximum depth of 10. Additionally, the function must handle empty or null inputs without errors. For edge cases, you need to ensure that your function works correctly for completely empty inputs, such as, or none. It should gracefully handle mixed or unexpected input types and avoid crashing in these scenarios. Finally, when dealing with large inputs, your function must maintain acceptable performance, and for unrecognized formats, it should return a valid response like unable to process. This ensures that the solution is robust, deterministic, and capable of handling a wide variety of scenarios effectively. When faced with LeetCode problem number 2023, the absence of a clear problem statement presents a unique kind of challenge. Here, we need to focus on analyzing the constraints and making reasonable inferences from the available context. To tackle this, we've considered three potential approaches. The first is the brute force approach, where we simulate solutions for various problem types such as array manipulation, string processing, or graph traversal, and test these against diverse edge cases. The intuition behind this method is to create a robust solution that works across a wide range of inputs. However, the downside is that this approach can become highly computationally expensive, especially when dealing with a large or ambiguous problem space. Next, we consider pattern recognition and generalization. Here, the idea is to analyze the structure of the inputs and outputs, looking for patterns or clues that might point to a specific problem category. For example, if the input looks like an array, we might test for operations like sorting or prefix sums. This method is particularly useful because many coding problems fall into well-known categories. However, it does require meticulous inspection and can fail if the problem doesn't match any familiar patterns. Lastly, we have adaptive algorithms. This involves designing a solution that evolves based on runtime feedback, using test cases to iteratively refine the approach. While this method mimics learning the problem over time, it can be resource-intensive and might not always lead to convergence on the correct solution. The adaptive algorithm approach offers an intriguing way of addressing the uncertainty in problem number 2023. By treating each test case as an opportunity to refine the solution, we essentially learn the problem through trial and error. However, the trade-off here lies in its potential computational cost and the lack of guarantees that it will converge for every possible problem scenario. After evaluating all three approaches, the most promising strategy is a hybrid of pattern recognition and adaptive algorithms. This combination leverages the strengths of both methods while minimizing their individual shortcomings. There are several reasons why this hybrid approach stands out. Firstly, coding problems typically fall into recognizable categories, and identifying patterns within the input or output can significantly narrow down the solution space. Secondly, incorporating adaptive techniques allows us to refine our understanding of the problem as we receive runtime feedback, making it a dynamic and iterative process. While this hybrid strategy does involve some manual intervention and computational overhead, it strikes a balance between robustness and efficiency. The process can be summarized in 3 steps. Start by analyzing the input and output to hypothesize the problem type, then implement a generalized solution tailored to this category, and finally, iteratively refine the solution using runtime results and test cases to validate each iteration. This hybrid approach emphasizes adaptability while ensuring that we remain focused on efficiency. By iterating between pattern recognition and runtime feedback, we can effectively handle the ambiguity of problem number 2023. The iterative nature of this method allows us to refine our hypotheses and solutions as we gain more insight into the problem's structure. This balance between methodical analysis and dynamic adjustment makes it a fitting strategy for tackling an undefined or unclear coding challenge. Ultimately, this approach equips us to systematically address the uncertainty, making progress even in the absence of a well-defined problem statement. To begin solving any algorithmic problem, the first step is to understand the problem clearly. This means examining the input and output requirements. If the problem details seem incomplete, try to infer constraints and edge cases. For instance, if the problem involves processing a sequence of data like an array or string, consider what operations might be needed to achieve the desired goal, such as finding patterns or optimizing results. Next, define the input and output explicitly. Identify the type of input data, whether it's an array, string, tree, graph, or a number. For arrays, consider properties like size, element range, and whether duplicates are allowed. For strings, think about edge cases like empty inputs, case sensitivity, or the presence of special characters. Similarly, you should be clear about the output format, such as returning an integer, a list, or another data structure. Finally, identify potential constraints. For example, if the input is an array, the size might be constrained to values like 1 equals n equals 10 to the power of 4, and elements could be integers in a specific range. If the problem involves graphs, constraints might specify properties like connectivity or being undirected. These steps lay the foundation for approaching the solution systematically. Once the problem is understood, the next step is to choose an approach. Depending on the problem type, different algorithmic strategies can be applied. For example, a brute force approach explores all possibilities and is useful for small constraints. A greedy approach makes locally optimal choices to build a global solution. Dynamic programming, or DP, is well suited for problems that can be broken into overlapping subproblems, allowing for efficient solutions through memoization or iterative tables. Binary search is another powerful tool, particularly for searching in sorted data or optimizing solutions within a specific range. In the case of graph problems, algorithms like BFS, DFS, or Dijkstra's may come into play. After selecting an approach, the problem should be broken down into smaller, manageable subproblems. For instance, if the task is to find the maximum sum of a subarray, you might start by identifying all subarrays, computing their sums, and then tracking the maximum. If constraints are involved, ensure that your breakdown respects them. Finally, implement the solution by translating these logical steps into code. For example, a common array-based problem like finding the maximum subarray sum can be solved efficiently using Cadon's algorithm. The given code snippet demonstrates this, where the current sum and maximum sum are updated iteratively to achieve an O(n) time complexity. Cadon's algorithm, as shown in the code example, optimizes the process of finding the maximum subarray sum by iterating through the array just once. This greedy approach ensures efficiency by maintaining a running sum and updating the maximum value dynamically. After implementation, it's critical to test the algorithm against edge cases. For example, how does it behave with an empty input, such as an empty array or string? What happens with the smallest or largest possible input sizes? Special values, like negative numbers, zeros, or duplicates, should also be considered. Additionally, testing the algorithm on large inputs verifies whether it adheres to the expected time and space complexity. Optimization is another key step. For brute force solutions, look for ways to eliminate redundant calculations. Recursive approaches can often benefit from memoization to avoid recalculating sub-problem results. Space efficiency can also be improved by reusing variables instead of creating new data structures. For instance, dynamic programming solutions might reduce space complexity from O(n) to O(1) by overwriting variables when only the last state is needed. These steps ensure the solution is robust, efficient, and scalable. Key insights for tackling algorithmic problems include starting with clear constraints and edge cases. Clarifying these early prevents incorrect assumptions and helps guide your choice of algorithm. A simple brute force approach is often a good starting point, as it allows you to fully understand the problem before optimizing. Efficient data structures can also make a significant difference. For example, hash maps enable O(1) lookups, while heaps are useful for priority-based operations. Testing edge cases early in the process is another essential practice, as it helps catch potential issues before full implementation. When it comes to data structures, arrays are versatile for sequential data and can be paired with techniques like sliding windows or prefix sums. Hash maps are perfect for tasks like frequency counting or memoization. Stacks and queues are ideal for problems involving order or sequence, such as matching parentheses or performing BFS traversals. Graphs, depending on the problem, can be represented using adjacency lists or matrices. To visualize data flow, consider an array problem where elements are processed iteratively. For example, starting with an input array like 3, -2, 5, -1, you might maintain running sums or states to compute the desired result, such as the maximum sum or specific indices. For graph-based problems, the data flow often begins with converting the edges into an adjacency list. Traversing the graph using BFS or DFS allows you to explore its nodes systematically. During traversal, you can track visited nodes to identify connected components or compute shortest paths. Key operations common to many algorithmic solutions include efficient iteration, ensuring constraints are checked at each step, and leveraging optimization techniques. For instance, pre-computing results, sorting data, or applying memoization can significantly speed up certain processes. Edge case handling is equally important. For example, ensure the algorithm can handle empty inputs, such as an empty array or null values, without breaking. Single-element inputs should also be verified for correctness, as they represent the minimum input size. Finally, test the solution on large inputs to ensure it performs within the upper limit constraints. These practices, combined with a clear understanding of data flow and algorithmic operations, equip you to tackle a wide range of problems effectively and efficiently. Here, we begin by outlining a Python solution for a classic problem involving finding all unique triplets in an array that sum up to 0. The solution is implemented within a class named solution and a method called 3sum. First, the input array, nums, is sorted to make it easier to handle duplicates and efficiently find triplets. We then declare an empty list named result to store the triplets that meet the condition. The main part of the solution involves iterating through the array using a for loop. For each number in the array, we skip duplicate values by checking if the current number is equal to the previous one. Once we ensure we are working with a unique number, two pointers are initialized, left, which starts just after the current number, and right, which starts at the end of the array. These pointers will help us explore potential triplets. Inside a while loop, we calculate the sum of the current triplet using the pointers and the current number. If the sum equals 0, the triplet is added to the result list. After that, both pointers are adjusted to avoid duplicates and continue searching for other valid triplets. Once the sum is processed, the loop checks if there are any further duplicates to the left or right of the current pointers. If duplicates are found on the left pointer is increment to skip over them. Similarly, if duplicates are found on the right pointer is decrement. If the triplet sum is less than 0, we know we need a larger value to reach 0, so the left pointer is moved forward. Conversely, if the sum is greater than 0, the right pointer is moved backward to reduce the sum. This process continues until the left pointer meets or surpasses the right pointer, indicating that all valid combinations for the current number have been explored. Finally, once the outer loop completes and all numbers in the array have been processed, the result list containing all unique triplets is returned. This approach ensures that the solution is both efficient and avoids duplicates, leveraging sorting and the two-pointer technique to achieve the desired outcome. Here, we begin by importing necessary libraries and defining the solution class. Inside the threesum method, we first sort the input array nums to make it easier to handle duplicates and use the two-pointer technique. Next, we initialize an empty list called result to store our triplets that satisfy the condition of having a sum of 0. We then start iterating through the array with a for loop. The variable I represents the current number we're considering. To avoid duplicate triplets, we include a check to skip over numbers that are the same as the previous iteration's number. After this, we initialize two pointers, left, which starts just after I, and right, which starts at the end of the array. These pointers help us explore potential triplets efficiently. Inside the while loop, we calculate the sum of the current triplet using nums, I, nums, left, and nums, right. If the sum equals 0, we add this triplet to the result list. After that, both pointers are adjusted inward, left is increment, and right is decrement. To prevent duplicates, we include additional checks to skip over repeated numbers at the left pointer by advancing it until it points to a new number. We continue to handle duplicate values by including a similar check for the right pointer. This ensures that repeated numbers at the right end are skipped by decrementing the pointer until it points to a distinct value. If the current sum is less than 0, we increment the left pointer to move toward larger numbers, as the array is sorted. On the other hand, if the sum is greater than 0, we decrement the right pointer to move toward smaller numbers. The process continues until the left pointer is no longer less than the right pointer, at which point the while loop ends for the current I. The outer for loop then moves to the next index in the array, repeating the same logic for the next number. Once all potential triplets are evaluated, the method finally returns the result list, which contains all unique triplets that sum to 0. This implementation efficiently combines sorting, the two-pointer technique, and duplicate checks to ensure we meet the problem's requirements. To solve this problem, we start with the input array nums equals -1, 0, 1, 2, -1, -4. The first step is to sort this array, which gives us -4, -1, -1, 0, 1, 2. This makes it easier to identify unique triplets and process the array efficiently. We then initialize an empty array called result to store any valid triplets we find. Now, we begin iterating through the sorted array with an outer loop. Starting at index I equals 0 where nums, I, equals -4, we set two pointers, left equals 1 and right equals 5, the ends of the array beyond the current index. Calculating the sum of these three values, current underscore sum equals -4 plus, -1, plus 2 equals -3, we see that the sum is less than 0, so we move the left pointer to the next position. This process repeats for the next sums, -3, -2, and -1, each time moving the left pointer forward. Once left reaches right, we exit this iteration since no valid triplet was found. Moving to the next index, I equals 1 where nums, I, equals -1, we reset the pointers to left equals 2 and right equals 5. Here, the sum of the triplet is current underscore sum equals -1 plus, -1, plus 2 equals 0. Since this equals 0, we add the triplet, -1, -1, 2, to the result array, then move both pointers inward. Afterward, the sum of the next triplet, -1 plus 0 plus 1, is also 0, so we add -1, 0, 1 to the result. At this point, the left pointer surpasses right, so we exit this iteration of the loop. As we continue, at index I equals 2 where nums I equals -1, we skip this value because it's a duplicate of the previous number. This ensures we don't calculate the same triplets multiple times. Next, at index I equals 3 where nums I equals 0, we set the pointers to left equals 4 and right equals 5. Calculating the sum of this triplet, current underscore sum equals 0 plus 1 plus 2 equals 3, we see that the sum is greater than 0. To reduce the sum, we move the right pointer inward to 4, but since the pointers now overlap, the inner loop exits. At this point, we have processed all valid indices and our final result for this example is result equals -1, -1, 2, -1, 0, 1. Now let's consider another example, where the input array is nums equals 0, 0, 0, 0. After sorting, the array remains 0, 0, 0, 0, and we again initialize an empty array result to store valid triplets. Starting the outer loop at index I equals 0 where nums I equals 0, we set left equals 1 and right equals 3. Calculating the sum of the triplet, current underscore sum equals 0 plus 0 plus 0 equals 0, we find a valid triplet and add 0, 0, 0 to the result. To avoid duplicates, we move both pointers inward, resulting in left surpassing right, so the inner loop exits. At index I equals 1, we skip processing because nums I is a duplicate of the previous value. This ensures no duplicate triplets are added. After processing all indices, the final result for this example is result equals 0, 0, 0. In this final example, the input array is nums equals 1, 2, -2, -1. After sorting, we get -2, -1, 1, 2. We initialize result as an empty array to store valid triplets. Starting with I equals 0 where nums I equals -2, we set left equals 1 and right equals 3. Calculating the sum of the triplet, current underscore sum equals -2 plus -1 plus 2 equals -1, we see that the sum is less than 0, so we move the left pointer forward. The next triplet sum is -2 plus 1 plus 2 equals 1, which is greater than 0, so we move the right pointer inward. At this point, the pointers overlap and the inner loop exits. Next, at index I equals 1 where nums I equals -1, we set left equals 2 and right equals 3. The sum of this triplet, current underscore sum equals -1 plus 1 plus 2 equals 2, is greater than 0, so we move the right pointer inward, and the inner loop exits again. After processing all indices, no valid triplets are found, and the final result for this example is result equals. In this section, we'll break down the time complexity of the solution into its main components. First, there's the sorting step, where the input array is sorted using the nums.sort operation. This sorting process has a time complexity of O n log n, where n represents the size of the input array. Sorting is a crucial pre-processing step that allows us to efficiently use the two-pointer technique later. After sorting, the algorithm iterates through the array using an outer loop. This loop runs n times, once for each element in the array, as it selects a number to act as the fixed value for the triplet. Within each iteration of the outer loop, the two-pointer traversal is used to find pairs of numbers that sum to a specific target. This traversal scans the remaining portion of the array, which, in the worst case, can involve up to O, n, elements for each iteration of the outer loop. These three components, sorting, iterating, and the two-pointer traversal, form the foundation of the time complexity analysis. Now, when we combine the outer loop and the two-pointer traversal, the time complexity can be derived by summing up the number of elements processed in each iteration. During the first iteration, the two-pointer traversal processes n elements. In the second iteration, it processes n1 elements, and in the third, n2, and so on, until only one element remains. This pattern forms the series n plus n1 plus n2 plus 1, which simplifies to O n squared when summed up. Adding this to the sorting step, which is O n log n, the total time complexity of the algorithm becomes O n log n plus n squared. However, for sufficiently large values of n, the O n squared term dominates, so we can conclude that the overall time complexity of the solution is O n squared. This efficiency is a significant improvement over other less optimized approaches. Let's now focus on the space complexity of the solution. The algorithm sorts the input array in place, meaning no additional space is required for the sorting operation. The array itself takes n space, where n is the size of the input. The result list, which stores the unique triplets, is the primary contributor to space usage. In the worst-case scenario, where all elements of the array are 0 and can form many combinations, the result list can grow to contain n squared triplets. Beyond this, the algorithm uses a constant amount of auxiliary space for variables such as left, right, current_sum, and loop counters. These variables add only 1 to the space complexity. Combining these observations, the dominant factor in space usage is the result list, leading to an overall space complexity of n squared. Analyzing the algorithm's behavior under different scenarios gives us a deeper understanding of its efficiency. In the best-case scenario, if the input array contains fewer than 3 elements, the algorithm terminates immediately without performing any significant computation. This results in 1 time and space complexity. For the average case, which involves a randomly ordered array, the sorting step takes n log n, while the two-pointer traversal contributes n squared, making the overall time complexity n squared. The worst-case scenario occurs when the array contains many duplicate elements or when all values are 0. This scenario results in the maximum possible number of unique triplets being identified, leading to both time and space complexities of n squared. Understanding these cases helps clarify the algorithm's performance under different conditions. To better appreciate the efficiency of the current approach, let's compare it to a brute force solution. A naive approach would involve generating all possible triplets, which requires examining every combination of 3 elements from the array. This generation step alone has a time complexity of n cubed, and checking the sum of each triplet takes 1. As a result, the total time complexity of the brute force approach is n cubed. The space complexity, however, remains n squared, as it still requires storage for the result list. In contrast, the optimized solution leverages sorting and the two-pointer technique to reduce the time complexity to n squared. This improvement makes the current approach significantly more efficient than the brute force solution, especially for large input sizes, while maintaining the same space complexity. Finally, let's summarize the mathematical derivation of the time complexity for the optimized solution. The outer loop runs n times, contributing n to the total complexity. For each iteration of the outer loop, the two-pointer traversal scans the remaining elements, which can take up to n operations per iteration. Sorting the array has a time complexity of n log n. When we combine these, the total time complexity is expressed as n log n plus n asterisk n, which simplifies to n log n plus n squared. Since the n squared term dominates for large values of n, the overall time complexity is n squared. On the space complexity side, the result list can grow to n squared in the worst case, while auxiliary variables require a constant amount of space, 1. Thus, the space complexity is also n squared. This completes the analysis of the algorithm's efficiency. When solving problems, there are some common mistakes that can trip you up. First, misunderstanding the problem scope is a frequent issue. Many candidates dive into coding without fully clarifying the constraints or considering edge cases. This can lead to solutions that fail for larger inputs or specific corner cases. To address this, always start by clarifying the problem requirements, constraints, and data bounds before writing any code. Another common pitfall is ignoring edge cases. Scenarios such as empty inputs, single-element arrays, or extreme values like maximum and minimum bounds are often overlooked. Neglecting these can result in runtime errors. The best way to avoid this is to explicitly test for these edge cases once you've written your initial solution. Lastly, overcomplicating the solution is another frequent error. For example, using a complex data structure like a hash map when a simpler two-pointer approach would suffice. To prevent this, start with a straightforward brute force solution and then optimize step by step. This ensures you build from a solid foundation and avoid unnecessary complexity. Now, let's focus on 2 more areas where mistakes often occur. Inefficient handling of large inputs is a major issue. Solutions with high time complexity, such as n squared, or worse, might pass smaller test cases but often fail on larger inputs due to time limits. To tackle this, analyze the time and space complexity of your approach early on and aim for an efficient solution right from the start. Another common mistake is off-by-one errors in loops, which can result in missing the last element or iterating too far. These kinds of errors often occur in problems involving arrays or strings. To prevent this, use clear and descriptive variable names, and be sure to explicitly test boundary cases. These small yet critical adjustments can significantly improve the reliability of your code. Success in coding interviews often comes down to your approach. Recognizing patterns in problems can save you a lot of time. Many problems fall into common categories like sliding window, binary search, or dynamic programming. The more you practice identifying these patterns during mock interviews, the quicker you can decide on an appropriate strategy. Also, remember that interviewers are less focused on whether your solution is perfect and more interested in how you approach the problem. Clearly explaining your thought process, even if you're unsure about the answer, demonstrates your problem-solving skills. Another key tip is to optimize iteratively. Begin with a basic solution, even if it's inefficient, and then explain your plan to refine it. This shows you're methodical in your approach. Finally, test cases are crucial. Always discuss edge cases and test your solution against them. This demonstrates that you're thorough and attentive to detail, qualities that interviewers value highly. To further strengthen your understanding, it helps to study related problems. For instance, toSum, which is LeetCode problem number 1, is a classic example that tests your ability to use hash maps efficiently. Longest substring without repeating characters, problem number 3, often requires sliding window techniques to solve. Another great problem is container with most water, problem number 11, which involves optimization strategies using a two-pointer approach. Lastly, there's 3Sum, problem number 15, which builds on toSum but introduces added complexity with sorting and handling duplicates. When solving these problems, you might start with a brute force approach. This is easy to implement and understand but is usually inefficient with time complexities like n squared. The optimized approaches, such as using hash maps or two-pointer techniques, are much more efficient, often achieving n or n log n complexities, but require careful implementation to handle edge cases effectively. For even more challenging problems, advanced techniques like binary search and sliding window can be invaluable. These methods are especially useful for patterns involving sorted data or substring problems. While they offer significant efficiency gains, they do come with their own challenges. Implementing these techniques requires a deeper understanding of the underlying concepts, and they can be harder to execute accurately under the pressure of a timed interview. However, with practice, these techniques become powerful tools that can set you apart as a candidate who's not only efficient but also well-versed in advanced problem-solving strategies. Thank you for watching. Today, we tackled the challenge of solving a problem with incomplete details, a skill that's incredibly useful in both interviews and real-world scenarios. Remember to practice solving ambiguous problems and focus on clear communication. If you enjoyed this, don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!